definition and classification of field effect transistor. So what is FET? FET is an acronym used for field effect transistor. It is a three-terminal unipolar device, either free electrons or holes, in which conduction is manipulated with the help of applied electric field. The name itself gives a brief idea about its working principle, field effect. These two words clearly indicate it is a transistor controlled by electric field. Thus, it is also referred as a voltage-controlled device in which only majority charge carriers are involved in the conduction mechanism. It comprises of three terminals, which are source, gate, and drain. The diagram labeled the three of the terminals. There are two types of field effect transistor, which is junction field effect transistor, JFET, and insulator gate field effect transistor, IGFET. Commonly used is MOSFET, metal oxide semiconductor field effect transistor. Let's see what JFET have. In JFET there are two types of channel, which is N channel and P channel. You can identify the type of channel by identifying the substrate for each channel like shown in the pictures. Here we can see how the physical diagram and the schematic symbol of JFETs. Then we will go through the MOSFET. For MOSFET there are also two types, which are depletion type and enhancement type. JFET and MOSFET will be elaborated more later. The FET are mostly used in the applications. So here is the comparison between FET and BJT. FET is basically a unipolar device which relies on either free electrons or holes, while BJT is bipolar device, meaning that it relies on two charges, free electrons and holes. The biggest difference between FET and BJT is that the input impedance of FET is very high, and due to that they are used as a buffer amplifier in many applications. Apart from that, the size of FETs are smaller compared to BJTs, making them commonly used in the integrated circuits. When we talk about the power consumption, the FET used less voltage when operated as amplifier than BJT. FET preferred in many high-power applications as well as in the computing applications because the power needed is minimal. Other than that, FET has more temperature stable and lower sensitivity to changes in the applied signal, which is slower response compared to BJT. Let's move on to the characteristics of field effect transistor. Basically, we're gonna go through the characteristics of JFET and MOSFET. Check it out. Figure shows the JFET characteristics curve. There are four regions involved, which is ohmic region, saturation region, cutoff region, breakdown region. First of all, ohmic region, also known as linear region, happen when the drain current ID has linear response to the changes of the drain source voltage VDS during this region. The junction field effect transistor, JFET, will act as voltage-controlled resistor, as the VG equal to 0. As the transistor reaches the maximum amount of current flow at a steady state, the region now known as the saturation region. During this region, the JFET, which controlled by the gate source voltage VGS, are at fully on mode. You can see through the figure that the drain source voltage has little effect, thus the curve turned to be almost flat. Opposite to the saturation region, device is in the OFF mode at pinch-off region. This occurs due to zero flow of current through transistor. JFET act as an open circuit as there is sufficient gate source voltage. VGs in the channel resistance is at maximum. Last but not least, the breakdown region. At this region, transistor resists the flow of current as the applied voltage exceeds the condition of the maximum value of the voltage. The voltage between the drain and the source VDS is high enough to cause the JFET's resistive channel to break down and pass uncontrolled maximum current. The table shows the differences characteristics of JFET and MOSFET. Next, as been mentioned earlier, JFET are divided into P-channel and N-channel. So, here is the comparison between them. N-channel JFET's pinch-off voltage, VP, is negative. Its gate-to-source voltage VGS also negative. Meanwhile, p-channel FETs VP and VGS are opposite to the n-channel. Nevertheless, the saturation region of n-channel FET occurs when VDS greater or equal to VDS saturation. As for p-channel FET, when VSD greater or equal to VSD saturation. Let's take a look at the current voltage characteristics for n-channel FET first. Based on the figure of n-channel FET's cross-section when the voltage gate is 0 with small VDS applied, the slope will increase linearly. The second figure shows the condition which there are small reverse biased gate voltage. Last but not least, the third figure shows the device condition as the gate voltage achieves pinch-off. The VDS has little or no effect to the slope. This table shows the differences between p-channel FET and n-channel FET. Let's continue with MOSFET. Basically there are two types of MOSFET, which is NMOS and MOS, which both of them can operate as enhancement and depletion mode. So here is the summary of their operation. We're going to elaborate and explain detail on the next slide. We begin with the enhancement mode of NMOS. As you can see on the figure below, there are two conditions. First, when the voltage gate to source, VGS are lower than the threshold voltage VT, and second, when the voltage gate to source, VGS are greater than the threshold voltage VTN. Okay, for the first condition with a small VDS applied, no electron inversion layer will be created. The drain to substrate PN junction is reverse biased, thus the ID drain current is 0. But for the second condition, also with small VDS applied, an electron inversion layer is created. The electrons flow from the source to the positive drain terminal. The conventional current enters the drain terminal and leaves the source terminal. A positive VDS drain voltage creates a reverse biased drain to substrate PN junction. Thus current flows through the channel region and not through a PN junction. The table below show ID versus VDS characteristics curve when VGS are greater than VTN with few categories stated. Slope of curve forms depends on the voltage drain inserted. Depletion mode of NMOS. Depletion mode means the carrier channel exists even at 0 gate voltage and channel region exists under the oxide when 0 volts are applied to gate. A drain to source current may be generated in the channel even with 0 gate voltage. A negative gate voltage must be applied to turn the device off. It induces a space charge region under the oxide, then reduce the thickness if n-channel region, the channel conductance and the drain current when the gate voltage is equal to the threshold voltage. The induced space charge region extends completely through the n-channel region, and the current goes to 0. A positive gate voltages create an electron accumulation layer which increase the drain current. As you can see at the figure of the characteristics curve, the saturation point is when VDS sat equal to VGS minus VT, and let's move on to the MOS. First we go through the enhancement mode. The charge carrier for MOS is holes. The substrate of MOS is N-type. The sources and drain areas are P-type. In order to induce the inversion layer of holes in the channel region, there are specifications required, which is negative gate bias, negative drain voltage and negative threshold voltage VTP. Holes flows from the source to the drain as P-type is the source of the charge carrier. The conventional current direction for the MOS is into the source and out of the drain as shown in the figure. For positive VSG and VSD, the gate voltage and drain voltage is negative respect to the source respectively, so here is the ideal MOSFET current voltage characteristics curve enhancement mode of MOS. Basically it is same as NMOS enhancement mode, just that the drain current is out of the drain and VDS is replaced by VSD. The saturation point is when the VSD, SAT, equal to VSG plus VTP. Non-saturation region occurs when VSD is smaller than VSD SAT, vice versa to the saturation region. Next, proceed to the depletion mode of MOS. As been mentioned earlier, the depletion mode means even when VGS equal to 0, the channel region of the charge carrier already exists. As for most the charge carrier are holes. Thus, in order to turned off the device, a positive gate voltage, VG, is required, hence the threshold voltage VTP are positive. Last but not least, here is the summary table of the previous lesson regarding characteristics of FET. Now, we arrive on the construction and the processing technique of the FET and MOSFET. First, we will see on the construction of FET part. As you can see, for N-channel FET, the wire is connected to each end of the N-channel. The drain is at the upper end and the source is at the lower end. There are two P-type regions that diffuse on the N-type material to form a channel. Both P-type regions are connected to the gate lead. Meanwhile, for P-channel FET, the wire is connected to each end of the P-channel. The drain is at the upper end and the source is at the lower end. There are two N-type regions that diffused on the P-type material to form a channel. Both N-type regions are connected to the gate lead. Next is the construction of MOSFET part. For PMOS, the N-type semiconductor structure considered as the substrate or the base. Dope the P-type to obtains the source and the drain terminals. The doping allowed to require the P-channel region between them. A thin layer of silicon dioxide is grown over the entire surface. Holes are made to draw ohmic contacts for drain and source terminals. Aluminium acts as a conducting layer is laid over the entire channel. And likewise, if the P-type semiconductor structure considered as the substrate or the base, it is known as MOS. Dope the N-type to obtains the source and the drain terminals. The doping allowed to require the N-channel region between them. A thin layer of silicon dioxide is grown over the entire surface. Holes are made to draw ohmic contacts for drain and source terminals. Aluminium acts as a conducting layer is laid over the entire channel. Okay then, we already know how the FET and MOSFET are constructed. We will see how actually the processing techniques or the working principle of these two types of FET. Okay, here for FET we can see that how the wire connected to the all terminals. For N-channel FET, the positive side is connected to the source terminal. The drain terminal receives the highest potential in comparison with the data in this N-channel FET. The junction formed due to the interaction of the drain and the gate terminal will be in reverse bias. Due to this reason, the width of the depletion region that is present near to the drain is greater in comparison with the source. Because of this condition, the majority of the charge carriers that are electrons flow can be seen from the terminal's drain to the source. As this potential at drain tends to increase, the flow of carriers increases, the flow of current also increases. But certain increment at the voltage at drain and source, the flow of current is stopped. The FET is generally known for the characteristics of controlling the current. The value of the input impedance is at peak in this transistor. When the FET is in its ideal mode, there is no current evidence at the gate terminal. For MOSFET part, the working principle was like this. Now you can see the figure above. Consider that VDS and VGS is a 0 volt. At this state, the MOSFET is remained stable but the depletion region formed. Consider that VGS as a positive. At this state, the positive voltage is applied to the gate terminals. The holes near the gate are repelled towards the substrate. This makes the MOSFET operates in the cut-off mode. Next, consider that VGS is greater than V threshold. At this state, all holes are depleted from the depletion region. Thus the gate attracts all the minority charge carriers. It causes the inversion layer near the gate to form. This inversion layer only contains of electrons. N-channel. If the N-channel enhances due to increase in the gate voltage, thus it called as enhancement type MOSFET. Consider that VGS is a positive. It supply a positive voltage to the drain. It causes the depletion region near the drain widen, which this is due to the reverse biased PN junction. When VDS is greater than VGS, the electrons from the channel field have a strong force of attraction towards the drain. This causes the electrons to start flowing from the source to the drain through the channel. The motion generates the drain current, which the motion flows from the drain to the source. When VDS increase, pinch off, it will reach a point where the channel will start to decrease at the drain terminal. Thus, the channel will get tapered and it will transform into a single point. After this state, which is pinch off, even if we increase the VDS, the ID will remain constant, where at this state, MOSFET is called B in a saturation mode. Then, let we see the application of field effect transistor. First is NMOS inverter. MOSFET can be used to switch currents, voltages, and power, perform digital logic functions, and amplify small time-varying signals. It also can be used as a switch in a wide variety of electronic applications. The transistor switch provides an advantage over mechanical switches, in both speed and reliability. The transistor switch in this section is called an inverter. If Vi is smaller than Vtn, the transistor is in cutoff and it equal to 0. There is no voltage drop across RD, and the output voltage is VO equal to VDD. Also, since it is 0, no power is dissipated in the transistor. If Vi is greater than Vtn, the transistor is on and initially is biased in the saturation region, since VDS greater than VGS minus Vtn. As the input voltage increases, the drain to source voltage decreases, and the transistor eventually becomes biased in the non-saturation region. When Vi equal to VDD, the transistor is biased in the non-saturation region. VO reaches a minimum value, and the drain current reaches a maximum value. The current and voltage are given by these formula. We will try this problem to test our understanding. Design the size of a power MOSFET to meet the specification of a particular switch application. The load in the inverter circuit in NMOS inverter circuit is a coil of an electromagnet that requires a current of 0.50 when turned on. The effective load resistance varies between 8 and 10, depending on temperature and other variables. A 10 V power supply is available. The transistor parameters are K'(N) equal to 80 microampere over V squared and Vtn equal to 1 volt. To solve this kind of problem, bias the transistor in the saturation region so that the current is constant and independent of the load resistance. The minimum VDS value is 5V. The value needed is VDS greater than VDS sat equal to VGS minus Vtn. If the transistor is biased at VGS is 5 volt, then the transistor will always be biased in the saturation region. Then the calculation is as you can see here after substituting the value given. This will yield W over L equal to 781. The maximum power dissipation in the transistor occurs when the load resistance is 8 and VDS equal to 6 volts. Then P max equal to VDS max multiply by ID, and insert the value given and the answer is 3 watt. Next is digital logic gate. For this application, a second transistor is connected in parallel, as shown in figure 2. If the two inputs are 0, both M1 and M2 are cut off, and VO is 5 volt. When V1 is 5 volts and V2 is 0, the transistor M1 turns on and M2 is still cut off. Transistor M1 is biased in the non-saturation region, and VO reaches a low value. If we reverse the input voltages such that V1 is 0 and V2 equal to 5 volt, then M1 is cut off and M2 is biased in the non-saturation region. Again, VO is at a low value. If both inputs are high, at V1 equal to V2 equal to 5 volts, then both transistors are biased in the non-saturation region and VO is low. Table 1 shows these various conditions for the circuit in figure 2. In a positive logic system, these results indicate that this circuit performs the NOR logic function, and, It is therefore called a two-input NOR logic circuit. In actual NMOS logic circuits, the resistor road is replaced by another NMOS transistor. So let's us solve this problem. Determine the currents and voltages in the digital logic gate for various input conditions. Consider the circuit shown in figure 3.46 with circuit and transistor parameters RD equals 20K, NOTS equals 0.1 mA/over V squared, VTN equal to 0.8 volts, and lambda is 0. Here the solution for V1 equals V2 equals 0. Both M1 and M2 are cut off and VO equal to VDD, which is equal to 5 volts. For V1 equal to 5 volts and V2 is 0, the transistor M1 is biased in the non-saturation region. Using the equation below we can find the VO. After that automatically we can substitute the value of VO in the equation below and get the value for current. Next for V1 is 0 and V2 equal to 5 volts. We have VO as 0.29 volts and I are equal to ID2, which is equal to 0.236 milliampere. When both inputs go high to V1 equal to V2 equal to 5 volts, we have IR is equal to ID1 plus ID2, or the equation below, which can be solved for VO to yield VO equal to 0.147 volts. Finally, the currents are defined. And the last one is MOSFET small signal amplifier. The MOSFET can amplify small time varying signals. It is a common source circuit in which a time varying signal is coupled to the gate through a coupling capacitor. The load line is determined for Vi equal to 0. A particular Q point can be established on the load line by designing the ratio of the bias resistors R1 and R. Assuming that Vi equal to Vi sent, the gate-to-source voltage will have a sinusoidal signal superimposed on the DC quiescent value. As the gate-to-source voltage changes over time, the Q point will move up and down the line, as indicated in the figure. Moving up and down the load line translates into a sinusoidal variation in the drain current and in the drain-to-source voltage. The variation in output voltage can be larger than the input signal voltage, which means the input signal is amplified. The actual signal gain depends on both the transistor parameters and the circuit element values. Now, we will go to basic field effect transistor part. First is JFET amplifier, which uses one or more field effect transistors. There are three types of FET amplifier: common drain amplifier, common gate amplifier, and common source amplifier. For common drain amplifier, the drain is common to both input and output. It is also known as source follower. While common source amplifier, the source is common to both input and the next is common gate amplifier. The gate is common to both input and output. There are some differences of circuit for these three types of JFET amplifier. For common source, it provides a medium input and output impedance levels. Both current and voltage gain can be described as medium. The output is the inverse of the input. Okay, let's check out for common drain. This amplifier, also known as the source follower, as the source voltage follows that of the gate, which this offering a high input impedance and a low output impedance, and it is widely used as a buffer. Common gate amplifier provides a low input impedance and offering a high output impedance. For this state, although the voltage is high, the current gain is low, thus the overall power gain is low. Besides, for this configuration, the input and output are in phase. Here is a summary of the FET configuration. As you can see, the table shows voltage gain, power gain, current gain, input resistance, output resistance, and input or output phase relationship for those three types of FET amplifier. MOSFET amplifier can produce an output signal which is an amplified magnitude of the input. In order to work, MOSFET has to be connected in the common source configuration. MOSFET has to operate in its saturation region, and MOSFET needs to be biased around a centrally fixed Q point. This amplifier highly dependable on transconductance and drain resistor. The figure shown is the example amplifier in most common source circuit, with a time-varying signal, is coupled to the gate. Now we will see how the MOSFET amplifier operating. First, we will provide a small signal with a time varying. Apply the DC bias at gate input. Once correctly biased in the saturation region, then the drain current ID varies as a result of the gate to source voltage VGS. The drain current is called saturated. MOSFET, the electrostatic field created by the application of a gate voltage, enhances the conductivity of the channel above this value. Then, the drain current increases in proportion to bracket of VGS minus VTH squared in the saturation region, allowing IT to operate as an amplifier. When a small sinusoidal signal, VGS, is applied to the MOSFET gate, resulting in a fluctuation of drain current synchronous to the applied sinusoidal input. For the small signal VGS, transconductance slope GM equals dID over dVGS, and for drain current amplitude, ID equals GM multiplied by the difference of VGS. Drain resistor RD can control the drain current and the drain voltage using the equation VDS equals VDD minus ID multiplied by RD. We can find AC output signal with VDS equals negative difference of ID multiplied by RD equals negative GM multiplied by VGS multiplied by RD. Formula for amplified voltage gain is equals negative GM multiplied by RD. We move to how does the direct current operating for basic MOSFET amplifier. The figure shows the simple enhancement mode common source MOSFET amplifier configuration. This MOSFET amplifier uses single supply at the drain. Basically, for normal operation of MOSFET, no current will flows into the gate terminal. However, for this case there are resistor divider which can generates the required gate voltage. Then we must know step-by-step calculation of this configuration. As you can see, the formula for VDD equal to IDRD plus VDS plus IDRS. And you can simplify the formula to get the value for RD and RS as shown. For MOSFET's gate to source voltage, VGS is given as VGS equal to VG minus IS, RS. For proper operation of the MOSFET, VGS greater than VTH, since IS equals ID, the gate voltage, VG is therefore equal to. By using this formula VGS equal to VG minus ID RS. And then when simplifying and manipulating the formula we will get the formula for VG which is equal to VGS plus VS. Set the MOSFET amplifier gate voltage to this value. By select the values of R1 and R2 within the voltage divider network to the correct values. The larger the R1 and R2 value, reduce the I squared R power loss, and increase the MOSFET amplifier's input resistance. The formula for voltage division is given as MOSFET amplifier gate bias voltage, VG equal to VDD multiplied by R2 over R1 plus R2. This voltage divider equation only determines the ratio of the two bias resistors, R1 and R2, and not their actual values. Okay, now, how to make a simple common source amplifier using N-channel single MOSFET. Firstly, MOSFET have to achieve DC biasing condition which require voltage divider, constructed using R1 and R2, drain resistor and source resistor. There are two coupling capacitors are used to compensate the cut-off frequencies, and to block the DC coming from the input or getting to the final output. Three resistors that associated with VDD, RD, MOSFET's internal resistance and RS. If we apply Kirchhoff's voltage law, VDD equals voltages across these three resistors. By using Ohm's law, voltage across RD is V equals ID multiplied by RD. Voltage across RS is Vs equals ID multiplied by RS. For the MOSFET, the voltage is VDS. Now as per the KVL, VDD equals ID multiplied by RD plus VDS plus ID multiplied by RS. VDD equals ID multiplied by bracket of RD plus RS, and then plus with VDS. RD plus RS equals VDD minus VDS over ID. We can further evaluate IT as RD equals VDD minus VDS over ID, negative RS. RS can be calculated as RS equals versus over ID. Other two resistors' values can be determined by the formula. VG equals VGS plus VS. VG equals VDD multiplied by the bracket of R2 over R1 plus R2. We can simply get the values by finding out the equivalent resistance of the DC bias divider and then selecting the desired cutoff frequency. The formula will be C equals 1 over 2 pi F requirement.